people hear me okay?
Yes, you are clear.
Okay, great. All right, so I will now take it over and give a bit more introduction on CBC searches and matched filtering. So here is kind of everything I am hoping to cover today. I'm going to start with just a really brief recap again of compact binary sources and waveforms. Of course, Maya just gave a really great talk on that, but I'll just say a few things that are relevant for the rest of the talk. So first of all, again, as Maya described really well, compact binary coalescences are mergers of the densest objects in our universe. So that means black holes and neutron stars. When these things orbit each other, they're going to emit energy as gravitational waves. And this causes the orbit to shrink and speed up. This makes more gravitational waves be released. And eventually we get this runaway process that leads to the merger and ring down. So we can model these waveforms in sort of three stages: the in-spiral, merger, and ring down. And these waveforms for compact binary coalescences really depend on the intrinsic parameters of the source. So that means the component masses and the spins. So you can see in this figure how mainly the masses have a really large effect on the waveform, and in particular, the duration of the waveform. So for low mass systems like binary neutron stars, you can see the waveform might last several minutes. But as we go up into higher mass systems like binary black holes, the waveforms might only be a second or a few seconds long. And so just maybe keep in mind how these unknown parameters really affect the shape of the signal. Okay, so now I will get into a bit of basics about matched filtering and kind of define what matched filtering is. First, I want to give an introduction on the LIGO data itself. What we have is a discrete time series of strain data, and we assume that this data always is going to include a noise component. And then at any time, the data may also contain a signal, but of course that presence of the signal is unknown to us. So we'll also make some assumptions about the noise. First of all, we assume that our noise is going to be stationary. So that means that the noise properties won't change in time. And if you looked at a chunk of data from now versus an hour from now or 2 weeks from now, with the stationary assumption, we're going to assume that those would all be basically identical. The other assumption that we make is that the noise is Gaussian. So this means that if you imagine that you had many, many identical detectors and they were all producing this noise at the same time, you could look at the distribution of those values and you would find that they follow a Gaussian distribution. And then with the stationary assumption also, we can easily say that, no matter what the mean of that Gaussian distribution is, we can easily transform the data to have a zero mean just by subtracting out whatever the constant mean is. So these are the assumptions we're going to start with. And with that matched filtering, if we have an assumption that we know what the signal looks like, we have basically what we call a template waveform, which is a model of the signal. We can use matched filtering to identify signals in the data. What this is just a correlation of the template with the data. So that means that we're taking the template and we slide it along the data. And at every point in time, we calculate the overlap between the template and the data. And the output of that process is what we call the signal to noise ratio, or SNR time series. And so you can see just kind of mathematically how this is defined both in the frequency domain and in the time domain. And here I have this really nice little movie that was made by Ryan McGee. This demonstrates how matched filtering works. So you can see we have our data in blue, and then we're going to be sliding the template in black along the data. And then at the point where a signal is kind of buried in the data, we get this really nice discernible peak in the SNR time series. And so this, I think, really demonstrates the benefit of matched filtering, which is that, the signal is pretty much invisible by eye. We really can't tell if there's a signal there or where it is. But by using the matched filter, it becomes really clear. And we get this, what we call a trigger, which is a peak in the SNR time series. And so once searches identify these triggers, then we can go on to assess the significance of the triggers. We can form coincidences, which means finding triggers at the same time among multiple detectors. And eventually these become our gravitational wave candidates. All right, so now let's talk about constructing the template banks. So one thing that I glossed over a little bit in the past few slides is that we have this assumption that we know what the signal looks like. We have a template waveform. Of course, for CBC waveforms, we can model the waveforms analytically or numerically, but as I mentioned in the beginning, these waveforms really depend on the masses and spins of the source, which is at the start unknown to us. We don't know what masses and spins we might necessarily be looking for. So we can't just pick one template and match filter the data and be done. Instead, what we have to do is construct what we call template banks, which means basically we choose a parameter space that we're interested in, so a range of masses and spins, and we're going to construct templates covering this entire range. And then we'll filter all of those templates. And so the question there becomes, how many templates do we need to construct? The idea is that if we have a signal that happens to perfectly match the template that we're using, we will get an optimal SNR from the filtering. But any mismatch in the parameters between the signal and our template will cause an SNR loss. So what we do is construct a really dense grid of templates all across our parameter space. And we choose this grid such that any real signal will be close enough to a nearest neighbor template so that our loss in SNR is sufficiently small. We usually just pick some percent of SNR loss that we're kind of okay with losing in the beginning. Maybe something around 3% might be typical. And we construct the template bank to be that dense. And so to make a template bank that covers the full binary neutron star black hole binary, and binary black hole parameter space, we can easily end up with hundreds of thousands to millions of templates that we have to filter. And filtering this many templates is going to pose a really significant computational burden. And so this is something that I'll talk about a little more at the end of the talk, is how do CBC searches kind of handle this computational burden and make the search feasible. All right, so now that I've kind of introduced all the basics of matched filtering and constructing the template banks, I want to go back and revisit some of the assumptions that I made about the LIGO data. So what we had kind of started with was this idea that the LIGO data is stationary and Gaussian. Unfortunately, neither of those are actually true. What we have is non-stationary, non-Gaussian data. And in fact, the only characterization of the LIGO noise that we have is from our observations. And so to get a more realistic picture of what the LIGO noise looks like, what we usually consider is this power spectral density, or PSD, which is shown in this figure. You can think of this as basically a measure of the sensitivity of the detectors. The lower these lines are, the more sensitive the detector is going to be in that frequency band. And this also shows the distribution of the power in the noise across frequency. So the first thing that I want to touch on is that our noise in LIGO is actually colored noise. So this means it has this distinct shape across frequency bands, whereas white noise would have a flat shape across all frequencies. And so what we want to do before filtering is to whiten the data and the templates, which basically means dividing out this PSD. And so that's shown here in these equations, and then we'll indicate a whitened quantity by this little hatch. And so when we do the matched filtering, we're actually doing it with the whitened data and templates. Okay, the next property of the noise is non-stationarity. So first of all, the LIGO noise can and does vary over long time scales. So that means it could be hours to days or week time scales. And this can just be affected by lots of things, maybe human activity or the weather even could affect this. And so the way this affects the searches is that basically in order to whiten our data, we need this measurement of the PSD. If the data was truly stationary, we could just measure the PSD once and know it forever and always use that one PSD. But since the noise properties are going to be changing in time, the searches have to continuously track the PSD and remeasure it and keep updating that quantity so that we can whiten the data accurately. The next property is non-stationary on short timescales. So these are what we refer to as glitches, and they're basically just short duration, non-Gaussian artifacts in the data. You can see what it looks like if we are matched filtering data that includes a glitch in this video here. And glitches can be really a big problem for matched filtering searches because you can see how even though this glitch really looks nothing like a real signal, it can still ring up these really loud peaks in the SNR time series. So the real CBC searches have to find methods of distinguishing these glitches from true signals. And that's another thing that I'll talk about in the rest of the talk. Oops. Okay, so now for the rest of the time, I want to go into some more details on the implementation of these matched filtering searches with the real search analyses that we have. So GST-LAL, MBTA, and PyCBC are the three that I'll talk about. And I'm going to just mostly focus on GST-LAL because that's the one that I work on. But I'll also talk about a few of the differences in the way that MBTA and PyCBC do matched filtering. So in practice, the search pipelines have this problem of dealing with the non-ideal noise properties that I just introduced. And additionally, they have to find ways to make the search efficient and deal with this computational burden of filtering maybe millions of templates, and especially trying to keep up with the data and do that filtering in real time. And so first, I will talk about how GST-LAL handles all of this. So first is handling the non-Gaussian data. I'll discuss kind of three different solutions to this that GST-LAL uses. The first one is gating. This is something that's done before the matched filtering. So what this basically is that we look into the data and we find things that look like glitches. And if we see something that looks like a glitch, we can just take a small chunk of time around that data, replace that data with zeros, and just decide that we're not even going to filter it. We'll just remove it because it looks like a glitch and it's basically too dangerous. This can be a really powerful way of dealing with the non-Gaussian data, but the immediate problem is that we have to be really careful not to accidentally gate a real signal. And this can be especially a problem for the higher mass templates. So think about really heavy binary black holes. These can have waveforms that are extremely loud and very, very short, and they may only last a few cycles. And so these are really easy to kind of mix up with glitches. They really look very similar. And so this can be a big problem, is accidentally gating a heavy binary black hole waveform because we thought it was a glitch. And so because of that, kind of the second way that we handle this non-Gaussian data is with signal consistency tests. So this is something that's done after the matched filtering. The idea here is that from filtering, we don't just get this one single SNR peak, and that's all we have. Instead, we have the full SNR time series. So if we imagine taking a template waveform and we assume that we have a signal in the data that precisely matches that template, then we can make a prediction for what the SNR time series from filtering that data will look like. We can basically know ahead of time what signal shape we expect. And then from filtering the real data, we can compare the measured or observed SNR time series to that prediction. And for a real signal, we would expect to see that the measurement matches the prediction. Here you can see just an example of that in this plot. The blue line is our prediction, and the black line comes from matched filtering, a stretch of data where we've injected a known signal into the data. And so you can see in that case how well the SNR time series match. And so this gives us an indication that the signal is real, whereas for a glitch, the SNR time series would not look how we would predict. So the third way that GST-LAO specifically handles non-Gaussian data is with IDQ. So IDQ stands for Integrated Data Quality. The idea here is from our detectors, of course, we have our main strain channel where the gravitational waves show up, but we also have many other auxiliary data channels, and these can monitor lots of other information about the state of the detectors, but they're kind of blind to gravitational waves. So what IDQ does is it monitors these auxiliary channels and uses machine learning to assign a probability that at any time there is a glitch in that data. So then with GST-LAO, we can take those probabilities from IDQ and use them to either increase the significance of our candidates if IDQ tells us that this data looks clean, or if IDQ tells us that there's very likely a glitch, we can reduce the significance of our candidates. And this is something that currently is only used by the GST-LAO pipeline. Okay, so that's kind of how GST-LAO handles this non-Gaussian data and the noise properties. Now I want to talk about how GST-LAO handles this computational burden of matched filtering. What we use is called the Lloyd method. This stands for low latency online in-spiral detection. And this method was developed for the purpose of enabling real-time matched filtering and even early warning matched filtering. So what that means is that we're able to identify a signal in the data even before the merger occurs or before the coalescence time of the signal. And so this method consists of two sort of steps, which I'll talk about in more detail, but they're first time slicing and downsampling of our waveforms. And then second is what's called singular value decomposition, or SVD. And the whole idea of this method is just to reduce the computational burden, improve the efficiency, and ultimately lower the latency of the search. So the first step is the time slicing and downsampling. Here we are taking advantage of this CBC waveform property, which is that they all monotonically increase in frequency. So with time, the frequency is always increasing. The idea is that in order to accurately represent any waveform, you need to sample it at a sampling rate that's at least twice as high as the largest frequency component in your waveform. But if we sampled these waveforms at twice of 4096 hertz, That means that for this lower early part of the waveform, we would be severely oversampling it, which is just extra unnecessary computation. So instead, what we do is we take these template waveforms before the filtering, and we split them into time slices. And each of these bands has a different frequency range. So at the early part, the frequencies are really low. And then in this next range, they get a little higher. And at the end, we have the highest frequencies. In each of these slices, we can downsample, and so use a much lower sampling rate down here at the early parts of the waveform compared to at the higher part of the waveform where we have to use the full sampling rate. And this downsampling is really, really helpful to improve the efficiency of our search. Make sure that we're not doing unnecessary computations by oversampling the waveform, and it makes it possible to perform this matched filtering in low latency. So the next half of the Lloyd method is the singular value decomposition, or what we call SVD. So here we are taking advantage of the template bank property. So if you remember, we construct these template banks to be extremely dense over the full parameter space so that we can make sure we are not losing very much SNR. But because the template banks are so dense, we end up with a lot of redundant templates. They all look really similar, and maybe from template to template, there's just a very small change. And so if we filtered all of these, it would be a pretty redundant process. So instead, what we do is you can think of each of these waveforms as just a vector, and the full set of these waveform vectors covers the space of the parameter space that we chose. What we can do is reduce the set of vectors to a set of basis waveforms, which still cover the space, but all of the basis waveforms are linearly independent. And so there's a much smaller number of them. The set of basis waveforms can maybe be at least a factor of 10 smaller than the original size of the bank. And here's an example of what those basis waveforms might look like. They have these kind of crazy shapes that don't look physical at all, but they're all much more unique. And so we get rid of that redundancy. So the idea with SVD is that we can perform our matched filtering with these basis waveforms. And then at the end, we can reconstruct any of the original input templates by just doing a linear combination of the basis waveforms. And at the end of the day, this saves us computations, and this is really key in allowing us to do that real-time matched filtering. Okay, so now I will just briefly kind of talk about MBTA and PyCBC and the differences in the way that these searches do matched filtering. One of the main differences is that PyCBC and MBTA both regularly perform matched filtering in the frequency domain, whereas GST-LAL usually does matched filtering in the time domain. So the idea here is that if you're matched filtering in the time domain, to get the output or the SNR at any point in time, you have to do a convolution. You have to do this integral. But if you transform to the frequency domain, that convolution just becomes a multiplication. And so what MBTA and PyCBC do is they first take the time series data from the detectors. They do the fast Fourier transform on the data to get it into the frequency domain. Then you can filter just by doing this multiplication, and then fast Fourier transform back to get the SNR time series out. Okay, so then how do MBTA and PyCBC handle the non-Gaussian data? In a lot of ways, they do it similarly to GST-LAL. So they also use gating and the signal consistency tests, but each pipeline might differ in the kind of very technical implementations of these methods. And then the other thing is that MBTA and PyCBC don't use IDQ, but instead they use vetoes. So these are basically flags that are applied to stretches of the data, which indicate kind of our confidence that the data is clean or whether it includes a lot of glitches and it's basically not suitable for matched filtering. So MBTA and PyCBC use vetoes to determine when data has poor data quality, and they can use that information to assess their triggers. The other thing that MBTA does is they refilter all of their high mass templates without using gating. So the reason for this is because, like I said earlier, it's really, you have to be very careful with gating not to accidentally remove true signals from the data. And this is especially problematic for those really heavy binary black hole waveforms that can tend to look a lot like glitches. So in order to account for this, basically, MBTA will refilter all of those templates without gating first, so that they can be sure that they're not missing those signals. Okay, and then lastly, MBTA does what's called multibanding. This is really similar to GST-LAL's time slicing method. And in fact, the time slicing of GST-LAL is based on this multibanding from MBTA. What they do is they filter the data in two frequency bands, so a low frequency and a high frequency band, and they can construct their templates then in this low frequency and high frequency band. So they have two sets of templates and they filter them separately. And then at the end, they can reconstruct the real templates after the filtering. And again, it's the same idea as the time slicing. This just allows for a reduction in the computational cost of the filtering and allows the whole process to proceed much faster. Okay, so as a summary, CBC searches are looking for gravitational waves from merging black holes and neutron stars in the LIGO Virgo strain data. We are able to use matched filtering for these searches because we know what the waveforms will look like. Because we're able to model them, we can construct templates and then do this correlation between the template and the data in order to identify the signals. And we have the three real matched filtering searches, GST-LAL, MBTA, and PyCBC. And these each have their own technical implementations and methods in order to perform the matched filtering, improve the sensitivity, and reduce the computational cost of the search. So that's all I have, and I can take any questions.
Awesome. Becca, thank you so much for the great talk.